This question asks us to predict the trend in boiling points for a series of molecules, and explain how we did it. On reading the question, you should recall that the temperature at which a substance boils is affected by the intermolecular forces between molecules. Also, note that the central atom in each of the molecules belongs to group 15 on the periodic table. So when we're asked to predict the trend, we should explain what happens to the boiling points of the molecules as we move down the column. Now the plan is simple. Use your knowledge of the three main types of intermolecular forces, dispersion, dipole-dipole, and hydrogen bonding, to determine the trend in boiling points for the molecules we've been given. Okay, solve. First, let's take a look at dipole-dipole forces. If we look up the electronegativities of nitrogen, phosphorus, arsenic, and antimony, and compare them to hydrogen, we find that phosphorus, arsenic, and antimony have approximately the same electronegativity values as hydrogen. So pH3, ASH3, and SBH3 will all be essentially nonpolar. Also, there can be no hydrogen bonding forces in effect for these molecules, since there are no nitrogen, oxygen, or fluorine atoms involved. So the major intermolecular forces at play here are dispersion forces. We know that all molecules experience dispersion forces, but the strength of forces varies with molecular weight. As molecular weight increases, dispersion forces increase, and as intermolecular forces increase, the boiling point increases. So for the last three molecules, as you move down the column from pH3 to SBH3, the boiling point increases. Now we just need to figure out how NH3 fits in. If we only consider dispersion forces, NH3 is the smallest molecule, so it would experience the smallest dispersion forces, and have the lowest boiling point. But we have to consider the other two intermolecular forces. NH3 is a polar molecule. Nitrogen has a significantly higher electronegativity value than hydrogen, and the trigonopyramidal geometry of NH3 does not allow the three individual NH dipoles to cancel. So NH3 is a polar molecule and experiences large dipole-dipole interactions. This will increase its boiling point with respect to the other three molecules. Also, NH3 molecules can form hydrogen bonds between each other, making the boiling point even higher. Although NH3 only experiences small dispersion forces, this is a minor factor compared to the dipole-dipole and hydrogen bonding forces in effect. So the final trend in boiling points, as we move down the column, should be NH3 with a relatively high boiling point, dropping sharply to pH3, and increasing on moving to ASH3 and SBH3. If you could check your answer with the real values, you'd find that they were -33, -88, -63, and -17 degrees Celsius. So we've got the trend right.